This is Chapter 3, Discrete Random Variables and Probability Distributions. Our first definition is that of a random variable, and it's just a function that assigns a numerical value to every event in the sample space. We've seen this already. As in many random processes, the choice for the random variable is obvious. So, for example, if we roll a die, then that random variable x could be the value of the die. Or we could have fuel usage, and in that case we might define some random variable f, which would be the amount of fuel in the tank. And then we could have something that would be a part from a CNC machine, and in that case we might have some L as being the critical dimension in that particular case. So we want to make an important note then, and that is that in general, for any random variable x, we can use the sample space that's given by, well, that x is a subset of the sample set, which simply ranges from minus infinity is less than x is less than plus infinity. And if that is a discrete random process, then the sample set S contains all integers and x is called we would presume it would be called a discrete random variable. And if the random variable or random process is continuous, then S contains all real numbers and x is going to be called a continuous random variable. Now, let's note something on notation, because this can be a little bit confusing when you're in your book. If you look, there's a big X and there's a little x. Big X means it's a symbolic representation of the random variable. So, in some sense, this is kind of like thinking about a dimension, and let's say your dimension was length. Right, and so we know it's length, right? So that kind of says it has something to do with length, and this number says it represents a numerical value for a random variable x. So in this case, this is like saying, well, okay, we know its length and it's in inches. We don't want to put in that it's 4 inches or 8 inches or whatever. We just want to put that it's some x, some inches, right? Meaning that that's part of the length. And so sometimes we'll say things like the probability that x is equal to x. And of course that looks a little bit goofy, but it simply means that the probability of, like, let's say that this is the face of a die, and that it's going to be some numerical value, which would be like 2. So this is like the placeholder for that larger symbol or the dimension of what we're looking at, and this is a placeholder for the actual specific value of that particular item that we're looking at. So now we can say that a probability function, probability of some x, remember that's a placeholder for some specific number, for some discrete random process with a discrete random variable x, big X, is given by this sort of peculiar looking notation right here. So in other words, we're saying the probability that the face of a die might have a 2 on it would be the probability of rolling a 2, something like that. Sometimes it's called a probability mass function in some textbooks. So for an example, we could flip a coin and define a random variable, and notice here's our big random variable. That's sort of the face of a coin. Can be either a head or a tail, And in that sense, we can say the probability of getting either the head or the tail is a 0.5 for each one. So, and of course, we're going to call it a 0 for anything else, even though it could trivially sort of end up someplace else. So the probability, or the properties of the probability function, are pretty much what you would assume them to be. Think of this as something like, we're figuring out probabilities it's going to rain tomorrow. Well, it's got a range between 0 and, well, we say 1 here, and of course that means 100%. You can't get bigger than 100%. There's not a 110% chance it's going to rain tomorrow. But we know that the probability for any discrete random variable, such that that random variable is a subset of the sample set, is going to range between 0 and 1. And the summation of all those probabilities has got a total 1, or 100%. So notice that the probability function from tossing a coin satisfies these kinds of conditions. We add up, we can throw a tail, we can throw a head. Each one has a probability of 0.5. We add 0.5 and 0.5, and we're in good shape because that becomes 1. Now, the expected value of a discrete random variable is given by this nifty little equation right here. Okay, we can say we're going to throw a value, like let's say a head, right? And we know that what previously we had defined, let's go back here. Previously we defined, head is defined as a 0, and a tail is defined as a 1. We could do it the other way, it doesn't matter. But so we're going to say that if this is a tail and that's defined as a 1, and we'll say the probability of us throwing that 1 is going to be 0.5. So what I'm really trying to get at here is, what is the expected value if we're throwing coins a lot of times? We can say that it's going to be the particular value that we throw times the probability of us throwing that, and sum that all up over all of the different values that we can throw. So in other words, let me write that a little more neatly. So we'll sum up x from minus infinity to infinity of x times the probability of x, and this is actually a vitally important equation. So what you're simply doing is weighting each particular value by the probability that that value would be received, and adding those all together. So we want to notice that the expected value, which is this right here, is equal to the average, and, well, I could turn these two around anyway, but expected value and mean and average are all the same sort of thing. So note now that the units of the expected value are going to be the same as the units of the x themselves. So if you want to figure out the expected value of a throw of dice, of 2 dice together, then that should be in the same sort of numerical units as the throw of the dice themselves. So now let's move on a little bit to gambling and roulette, because, well, a lot of probability arose out of looking at gambling and gambling problems. So first off, let's go and look and see what is roulette.
Ashley, why don't you take a moment, get yourself composed, then we'll go over the rules of the game.
Are you sure you want to make this bet with your life savings?
Yeah, I'm assessing. I want you to know we would never knowingly condone or accept someone taking a wager of their entire life savings. But we know that this is a culmination of a grand adventure for you, and hopefully the start of many more interesting adventures. To that extent, once you're ready, just give me a head nod and we'll start it. Once the ball is in the track and spun, if you haven't declared yourself before the ball has traveled 2 times around the wheel, we'll call it a no bet, and we'll start again. Is this acceptable to you?
Yeah.
Good luck.
What colour then? I don't know. Too many decisions. Big lad. Like, is it? Okay. Great.
Okay, the deal now is if you have, let's say, it lands on a 3 and you have a 3, well, and you've placed a bet of something like $10, well, then you're going to win. And so at that time, it's the equivalent of as if you had placed 10 on all 36 of these different places, and then you would also place $10 there. So what you'd win actually is 10 times 38, right? And so you'd win $380 for your $10 bet. But let's say you bet $10 on a single number, it comes up on the wheel, and the payoff is going to be, well, 360. And the probability of that happening is going to be 1 out of those 38 different possible places that the ball could have landed on. Now, let's say that we want to figure out the expected value. That is what you would expect to win if you played for a really long time. So if that's the case, then, well, let's say that you bet $10 on the number 13, and you did that 38,000 times. So I'm not going to do this 38,000 times because it would drive us all nuts. But on average, 1,000 of those bets would win and 37,000 would lose, right? Because they'd be on some other places on the board. So your total payoff in that particular event is going to be, well, $360 for every time you win, which is going to be about 1,000 times. So that's going to be 360,000. And the total amount that is going to be paid is going to be $10 times 38,000, right? And that's $380,000. And the total gain then is going to be $360,000 minus $380,000, which is, well, there's something wrong with that gain because it's actually a loss. And per bet then, the expected value is just going to be, well, 20,000 divided by 38,000, and that's going to be minus 0.53, well, 53 cents. So it is a losing proposition for you, but in the long run for the house, it is a winning proposition. So the expected value, that $10 bet, is 53 cents, which is kind of not so good. And that's equivalent to saying that, that we can have 138. That's the probability of winning $350, plus what's the other outcome? It is that you could lose $10, and that sums to 0.53, which is 53 cents. And notice, what is this? This is actually the same that we had written earlier. It's this summation of x minus infinity to plus infinity, all the probabilities, right? We can either win or lose, and the probability of each, and so that's the expected value that we get right here, E of x. So I'm just going to write this in a little bit different way, and that simply says that the definition of the expected value, if you take all those outcomes, multiply each outcome by its probability of getting that particular outcome, and you'll find what the expected value is. So another value, or another example of expected value, is if we play roulette just a bit differently. As it turns out, we can bet on red, right? So instead of betting on a red or on a 1, we can actually bet on all reds. So a bet of red on roulette has a probability of 18 out of 38. You can count them and see, and of winning, but 20 out of 38 of losing because of these two little rascals right there. So the payoff for a $10 bet is $20, and that gives you a gain of $10. And the expected value for the $10 bet is just going to be, well, you can calculate the probability of each one happening, of winning or of losing, and that's minus 53 cents. Notice how we have this as losing. We're going to do another problem later on where I will say the odds of winning a certain amount are $1, say, and then I'll say you get nothing if you lose, and so then I say 0. So I'll be defining this number a bit differently. Here it is defined as the total loss. Later you'll see I'll be defining a total win, right? Or how much you would actually win. But that's, you can replay this if you're interested when we get to the later one. So the law of large numbers says that a fraction of trials having an event E approaches the probability of E as the number of trials increases. So we're really just saying number of trials having event E, right? Whoops. divided by the number of trials, and that becomes the probability of E. So now we can have roulette simulations if we were to do something like that. That's the equivalent of us playing lots and lots of games of roulette, which of course is what computers are very good at doing. So let's say we simulated having a $10 bet on red in roulette, and we did that 10,000 times and calculated the average gain. Well, it's a loss, right? So it's going to be negative. And we repeated this 10 times. Okay, that may take a minute to sink in, but if it doesn't, then you'll see what I mean, I think, in just a minute. Let's say that we also repeated the same experiment 1,000,000 times and repeated that 1,000,000-time experiment 10 times. Okay, now if we did that, so look at this. We're essentially figuring out the average gain over 10,000 bets and the average gain over 1,000,000 bets, right? And here we did this the first time, second time. Look at how different those are. Third time. But here you can see it really tightens up. And that's to be expected because we're using larger numbers. Now, let's learn a little bit of unexpected information about expected values. Let's say that you played 35 rounds of roulette and you're betting on one number every time. The expected value in that particular situation is going to be, well, we already calculated that out. We can win 1 out of 38 and we can lose all the other 37 times. And let's say that we did that 35 times. That's okay. Well, if we did that 35 times, don't you expect that we would take that value and multiply it by 35, and that would sort of be like our expected outcome there? Well, yeah, it is. So we'll just take that. We'll say it's 35 times all of this stuff right up here, which is minus 0.53. And that turns out to be minus 18.42. So overall, you're in the hole on average. But here's the interesting thing is that actually most people, even though on average people are in the hole $18.42, 61% of the people who are playing are actually still ahead. How can that be? Let's look at this. The probability of being ahead after 35 rounds, all you got to do to be ahead is to win at least one time. To win at least one time, well, that's the same as 1 minus the probability that you lost the other 35 times. So, well, let's see. Losing, you have a 37 out of 38, 38 chance of losing, right? And now let me rewrite that, 38. Okay, so you do that. That's your first try. You got 37 out of 38. Second try, it's going to be times the same thing, and then times the same thing. And actually, you're going to be doing that 35 times, right? That's 37 over 38 raised to the 35th power is the probability of losing all 35. So 1 minus that is the probability of winning at least one time, and that is 0.61. So that means 61% of the people have won at least once, so they're a little bit ahead. But the ones that were in the hole are like pretty much in the hole, and they make up for all of this. But that's just an interesting and kind of unexpected outcome of expected value.